Hey everyone, welcome back. Today we're talking about losses in switch mode power supplies. And the way we're going to do that is by looking at each individual component. So today we're starting with capacitors. And I assume you've all seen capacitors before. They look, in circuit drawings anyways, they look like this, right? Two parallel plates. And this value is usually specified with C. And sometimes you might even see this, right? Which is a polarized capacitor, right? So meaning you can only apply voltage in one direction across it. Cool. So yeah, the impedance is 1 over j omega, blah, 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 blah. But when we actually go to build these things, choices of materials affect the final properties of the capacitor. And it's not always this ideal thing, right? This is an idealized version. So let's look at the construction to understand what a real capacitor might actually have. So the way we're going to start is in kind of the most basic way possible, and that's with a parallel plate capacitor, right? So we have one plate with some lead dangling off of it, let's say, followed by some kind of dielectric, right? So we kind of have this sandwich thing going on, right? And then followed by another plate. Cool, followed with another lead, right? So this is the basic capacitor. This is like a parallel plate capacitor. And with this kind of construction, we're interested in basically three parameters. The first one is the area of the plates, A. The second is the distance between the plates, D. And then the third, let's use right again. The third is the permittivity of the material itself. Right, so in this case we write it with some relative permittivity times the free space permittivity. And it turns out that the final capacitance you get is equal to epsilon r epsilon naught A over D. And even though this is like the most simple capacitor, it really kind of contains the insight you need to understand how capacitors operate, right? There's two plates, some distance between them, and there's some area with some dielectric. And none of these materials in practice are ideal, right? So the metals are going to have finite conductivity. The dielectrics won't be perfect insulators, right? And maybe, their properties vary depending on the voltage applied to them, right? So it doesn't always end up being perfect. And as a result, we end up with non-idealities. So maybe a more realistic version of this capacitor involves a few more things. So one, we're using metals with finite conductivity, which means that there will be some kind of resistance associated with this capacitor. Usually we lump that into a single element, which we call the ESR, or the equivalent series resistance. Right? Finite conductivity, there's going to be some resistance. Furthermore, if we're carrying current in some wires, right, that connect to this dielectric material, well, we're going to be storing some energy in magnetic fields surrounding that wire, which means that these wires have some kind of inductance, which we refer to as the ESL. So the equivalent series inductance. Cool. And then you actually probably have the capacitance you expect, right? You have some C. However, this C is not necessarily constant, and it can vary with a lot of things, notably the applied voltage. Right, which is kind of weird, right? You expect that the cap should look like a cap regardless of the voltage you apply, but it actually changes the polarization of the dielectric material, kind of changes like the effective distance or whatever. Things vary, and the capacitance might actually be a function of the applied voltage, as well as things like temperature, a bunch of other things, right? So this cap is actually kind of variable to some extent, and that varies based on the construction. And then finally, this dielectric might not be perfect, imperfect insulator, which means some current might flow from the two plates, right? And we kind of model that with, I'll use a dotted line. We model that with a resistance in parallel with all this stuff, right? And this you might call the leakage resistance. And typically for a lot of capacitors, this is a very large resistance. It very closely approximates an open circuit, but it does affect, how long the capacitor can store energy when it's disconnected from other things, right? Eventually, this leakage resistance will just bleed off whatever power you're trying to leave in the capacitor. kind of makes them bad for long-term storage, right? Cool. So of these things, then there's a lot of variables. It all varies depending on construction, all these different values, right? ESR, ESL, C, whatever. The most important aspects, we might say, or the non-ideal aspects that we're going to talk about anyways, well, one is the loss associated with ESR. And the second that's kind of interesting and important that I kind of want to talk about is the self-resonant frequency. Self-resonant frequency. Cool. So, and this arises because we have some kind of tank, right? We have some kind of energy tank, right? We have an L and a C, and when these impedances are equal and opposite, well, the total impedance of this network goes to 0. And then you just see the ESR, basically. So that's an important part of capacitors, as well as this variable capacitance. Cool. So actually, ESR, funnily enough, even though it's the most important loss parameter potentially, ESR is often not given by manufacturers. Typically what they give is something called the dissipation factor. Which is tan delta. So this delta represents the angle between the resistance, ESR, and the capacitance, C. So it turns out that ESR you can calculate from tan delta, and it's equal to tan delta over omega C, right? So it's some frequency dependent resistance, right? So they don't give you ESR directly because it actually varies over frequency. So it's kind of more accurate to give this number. Cool. So let's actually calculate loss, or let's figure out how you might calculate loss on a capacitor. Well, if this is kind of the loss model we're going to be considering, right? So the other stuff is there for sure, like the inductance and the leakage, but what we're interested in really for calculating the majority of the loss that this thing produces is the ESR. So we can imagine that, some IC flows through here, IC of T, something that's charging up the capacitor and discharging it, whatever. And that current passes through this resistance, right? So we can come up with a function, some power loss as a function of time, P loss, and that would be IC of T squared times the ESR. Right, and so this is a time varying function, and it turns out that when you want to calculate loss with time varying functions and resistors, what you should use is the RMS. So that the P loss, capital P loss, the non-time varying loss, is the IC RMS squared times ESR. Right, so what this means, what I'm saying with this is you have to look at the cap current waveform. Right, so let's look at a common one. And this is I'm not saying like just memorize this equation. What I'm saying is look at the waveform, calculate the RMS, and then you can calculate the loss. So a common waveform, common IC of T, would be an output capacitor, right? That's a capacitor that you have in basically every single circuit. And for the buck, for instance, the capacitor current looks like this, right? When we have a direct energy transfer converter, this is what the current looks like. And this ripple it turns out is delta IL. And if you want to calculate the RMS, so IC RMS is equal to the root of the mean, right, of the square of the current, right? That's what RMS means. And you can figure out an equation for this, or you can look in the back of Fundamentals of Power Electronics, and it gives you an equation for this kind of waveform. And it turns out that this RMS current is simply delta IL over 3, right? So it's the delta of it's the ripple current divided by root 3, and that's the RMS current. And as a result, the P loss for this capacitor in this context, right, this model gives us the loss is delta IL squared over 3, right? I just squared both things, times ESR, right? And you kind of can choose the frequency that this is happening at some F. Cool. So yeah, that's kind of like the simple way of calculating loss for a capacitor, right? You look at the ESR and look at the current going through it. Find the RMS, square it, multiply it by the ESR, you have the loss. And what I want to point out here is that there are two kinds of failure typically that can happen. One, right, the other thing that you should be worried about with capacitors is electrical breakdown and also thermal breakdown. So electrical breakdown is simply when the applied voltage exceeds some maximum voltage specified in the data sheet, right? So maybe your cap is only rated for 16 volts. If you apply more than 16 volts, the cap is going to explode. So this is kind of easy to take care of. This other thing, which is actually related to loss, the thermal breakdown, is basically when the capacitor overheats. So when you have this kind of loss, right, you're going to create heat in the device, and thermal breakdown happens when the T of the capacitor exceeds some maximum temperature that the capacitor can operate at. This temperature of the capacitor is related to the power loss. So how is it related? Well, it's the ambient temperature plus the loss times this new parameter, thermal resistance. So beyond this loss just being important for efficiency, it's also important for, how, in what conditions you can operate the capacitor, right? So this R theta is what's known as the thermal resistance. So different capacitors will have different thermal resistances. And it has units of, well, maybe you can guess, degrees Celsius per watt. Right? So what this is saying is, what the thermal resistance says is how much the temperature will increase when a certain amount of power is dissipated on that device. Right? So if you lose 1 watt and the thermal resistance is 1 degree Celsius per watt, then the device will go up by 1 degree Celsius. Pretty simple, right? So when you calculate this loss, this is kind of the other side. Typically, you won't be very close to the maximum operating temperature, but sometimes you will, and you should pay attention. Cool. So these are kind of the important things with loss for capacitors, and I just wanted to go over a few different constructions. So this was taken from Wikipedia. Thank you, whoever made this plot. Thank you for making it freely available to use. And this just shows different ranges for different capacitor constructions. So we have ceramic capacitors, right, which are used everywhere, super common. We have electrolytic capacitors, again, super common capacitors. These are like those cylinder things with little legs sticking out. Those are electrolytic capacitors. Tantalum capacitors, supercapacitors, or ultracaps, those are kind of gaining a lot of attention right now. There's plastic film capacitors and power capacitors. What I want to point out with this is that the different constructions kind of follow this rough trade-off curve, right? So there's kind of this trend, right? Roughly. So what this trend is that for really high voltage, you can have low capacitance, and for really high capacitance, you tend to have lower voltage, lower blocking voltage, right? So supercaps can't be exposed to that high voltage, and if you have a really smaller capacitance, tends to be able to block higher voltages. And why does that happen? Well, it kind of makes sense from the construction, right? So if we look at this parallel plate capacitor, capacitance is inversely proportional to D, right? The distance between the plates. So as you decrease D, you get higher capacitance, but it also means that you can block less voltage, right? The two plates are closer together, breakdown is more possible, right? So that's what this trend is I'm trying to show you with this trend anyways. There's like higher blocking voltage, lower cap. Lower blocking voltage, higher cap. And these different constructions also have different effects on the other parameters. So this is, for instance, a ceramic capacitor. This is by KEMET. And ceramic capacitors are like layers of ceramic, right? So they're kind of sandwiches, ceramic layers. And in between those ceramic layers are actually the electrodes, or like the terminals, right? So you have one plate over here, and this plate actually extends into the ceramic however far. And then you have the other plate on the other side, right? And it also extends into the ceramic, right? So doing this, you kind of increase the effective area and decrease the distance to increase the capacitance for a given size, given dielectric. But it also limits the maximum blocking voltage, right? So this is a 0.1 microfarad cap. You're going to block 10 volts. Gives you the tan delta, right? So it's saying that tan delta is at max 10%. 10% of what? 10% of omega C. Cool. So there's some temperature, right? It tells you the maximum operating temperature, back to kind of thermal breakdown. And also insulation resistance, right? So this is like the leakage, right? The non-ideality of the dielectric. So there's two things I wanted to show you with this ceramic capacitor specifically. Ceramic capacitors are strong functions of applied voltage, right? So as the DC bias of on the capacitor increases, the capacitance decreases significantly, right? So if you go to like halfway, around 5 volts, you've lost 50% of your capacitance, right? That's something you should note when you choose a specific kind of capacitor for your application. Ceramic capacitors, you often need to stack a whole bunch of them to get the required capacitance that you want. And we can also look at the impedance versus frequency. So we have the impedance of the cap, right? Looks like a cap over here, minus 20 dB per decade. And then you approach the self-resonant frequency, the SRF, right? This is where the impedance of the inductance, ESL, and the capacitance are equal and opposite to one another, right? So they decrease, and you end up seeing only the impedance of the ESR here. Beyond this point, it looks inductive. Beyond this point, beyond the SRF, the capacitor actually looks like an inductor. It operates like an inductor because the ESL is dominant in that portion. On this side, right, it looks like a cap. So there's kind of a frequency range over which caps are actually useful as caps, right? Beyond the self-resonant frequency, no longer holds. And you can see the ESR here, right? So they said 10%. So the ESR max is 1/10 of the impedance of the cap, right? And that's kind of what you see here. This is like less than 10%. And that decreases up until a point, right? Eventually it starts increasing again, probably due to things like skin effect, and the effective resistance of the leads actually increases. You know, like the current tends towards the edges of the conductors at high frequencies, that kind of stuff. The ESR actually tends to increase. Cool. So again, this is kind of a typical thing you'll see with a lot of different capacitors, right? There's some ESR that decreases, and then eventually it starts looking like an inductor. That's common. And just to drive this home, what I wanted to show you is, again, from KEMET. No affiliation with KEMET. This is just to show you some interesting things. KEMET has a very interesting tool that you can use to analyze different capacitors. And this is one of the things they have. So I've plotted 3 capacitors of different construction, all 10 microfarad, 25 volt, and I've biased them at 12.5 volts. DC bias is 12.5 volts, halfway. So the ceramic capacitor actually has less capacitance than the two others, the tantalum and the tantalum polymer. So ceramic has less capacitance. We've chosen all the same thing, right? But the ceramic isn't 10 microfarads. It's something else because of the bias, because of the DC bias, right? And then so the ceramic reaches its self-resonant frequency and then starts looking like an inductor. But the inductance is actually less, smaller inductance than the tantalum and the tantalum polymer. Right? And just to be clear, moving towards higher frequencies indicates a smaller cap or a smaller inductance, right? So if this line shifts to the right, then it's a smaller cap. If this line shifts to the right, then it's a smaller cap, right? And towards negative infinity or towards 0 is larger cap, larger inductance. So the ceramic, even though it has the same parameters, so to speak, it's a smaller cap with a higher resonant frequency and a smaller inductance. The tantalums are pretty stable, right? But their self-resonant frequency, or this range where it starts looking more like an inductor, tends to be a bit more flat, right? Not so the Q isn't as high, but it's also at a lower frequency, right? So the DC, the lower frequency capacitance is more stable, but it doesn't operate quite as well as the ceramic for higher frequency. Furthermore, the ESR of these things are vastly different, right? So the tantalum, the straight tantalum, this green line, ESR of the tantalum, is higher, significantly higher than the regular tantalum at low frequency. And then the ceramic has the lowest ESR for a wide range of frequencies, right? And then even up to the self-resonant frequency, it's still lower. So this very low ESR might be really helpful for you depending on your application. So just be aware that different constructions result in very different behaviors. Cool. So that's it for now. Basically, we just looked at ESR and realized that we have to look at the RMS current through the cap, square that and multiply that by the ESR to find the loss. The loss is important because of thermal breakdown and efficiency. And we're going to kind of do a similar thing for the next thing, inductors. Cool, thanks.